Okay. So for today's webinar is actually a continuation from our previous webinar, which is the electromagnetic analysis for BPM motor. And today we're going to discuss about thermal analysis. So before we go anywhere further,
Yeah.
So this is all the list for all the Ansys product. So for the Ansys product we have mostly used is this three, which is the structure, fluid, and electronics. And for the AutoCAD, it is under electronics. So what else are there inside Ansys electronics product? So first of all, we have FHSS for this is a software for high frequency simulation. This one is a Ansys Maxwell for low frequency electromagnetic simulation. So we have SI Wave for electronic package. We have iSpec for thermal integrity. Now we're using the AutoCAD, and we also have a EMA 3D cable for simulating cable. We have also a Q3D extractor, EMA 3D charge, and Hertz filter solution. So if you want to know more about this product, you can go to Ansys website for more information. So next, what is Ansys Motor-CAD? We already discussed this from our previous introduction. So Ansys Motor-CAD enables engineer to evaluate motor topologies across the full top speed operating range to optimize their performance, efficiency, and size. So Motor-CAD is a template-based design tool for a fast multiphysics analysis of electric motors. So these are all the motor types that can be simulated inside AutoCAD. So this is all the template based for brushless permanent magnet motor, brushless permanent magnet motor, rotor motors, synchronous reluctance machine, switch reluctance motor, synchronous machine, induction machines, single phase induction machines, and permanent magnet DC, and also, finally the claw pole machines. So for today's demonstration, we'll be using the brushless permanent magnet motors. So we already discussed about EMAG simulation last week, which is the first template-based electromagnetic performance prediction. So for today, we're going to use this thermal model. So it's for thermal performance prediction and advanced cooling system for the motor. So for this demonstration, we'll be using the same design from previous webinar, which is the BPM. So later on, I'll show you how we edit this template. This is for the radial view, the axial view, and for the input data, we'll be adding the housing water jacket for cooling, and for the simulation, we'll see the steady state simulation and also the transient. And finally, will be for the result, we can see the schematic temperature, the radial and axial temperature. We can see the temperature for the whole motor. You can see all this temperature here. There's the number here. And we also can see the numerical result for the temperature for each of the component of the motor through this output data. And for the transient simulation, we can see the transient graph from the result of this simulation. So without further ado, I'll be opening Ansys Motor-CAD. So this is the simulation, our electromagnetic simulation from the previous webinar. So we just continue from there. So we can see here the motor type is still the same. We are using the BPM here. And for the model, we can change it to thermal. So you can see the parameters changing. So we can edit this parameter. So we are using this water jacket spiral here for the housing. And then we change the housing diameter. So if we right click on this housing diameter, you can see if you right click it, you can see it's changing, which means that is the housing diameter. We are going to changing that. So we change this to 252. And if we click enter, you can see the housing diameter change. And then we change the WJ channel length here. You see it's moving. So we change this to 10 and the height here to 5. Enter. So we're already changing the housing. And then next, what we're going to do is we go to the next is we go to the axial view of the motor. So for this, it's already changed to the water jacket spiral, and we change the shaft diameter F here to 20. Say 20. So to see what are we changing, we can right click it to see the moving part is the thing that we're changing. And then next is we're going to change the WDG outer F and outer right, front and rear. So we change this to 3. Enter. Next, for the axial dimension, we change the end cap length here, front and rear. So for this one, we change to 10. We change it to 30. Okay. And the end cap thickness here, we change it to 10. And then the WJ channel width here, and the spacing. So we change this to 30 and 35. So basically, we are good to go for the modeling of the motor. So we can also see the winding. So basically, we didn't change any winding here. We're using the same as the previous one. And we also can see we're going to change the input data. So we go to cooling and we click on this cooling system, the housing water jacket, and we change the ambient temperature to 65 degrees. And next, what else we're going to do is we go to the housing water jacket here. This is all the properties of the housing water jacket. We go to the flow option. We make sure it's a constant flow rate, and the fluid flow rate is the fluid volume flow rate is the 6.5. And then we go to the fluid flow. You can see here it will be the same as previous one, the 6.5, and we just change the inlet temperature to 65. The fluid properties, we use this EGW 5050, and we change this good. No untap cooling. We click on this active cooling only. Calculate here, and yeah, everything looks fine. So after this, you can see the geometry. You can see here is the 3D geometry of the motor. You can see the housing water jacket here, and the flow of the fluid for the cooling. Yeah, and then you might want to change the input data for the interface. We want the stator laminate lamp housing to have a good surface contact. And yeah, so that's pretty much it for the setting of the model. Now, what we're going to do is we go to first we go to the e-magnetics. So for this e-magnetic model, we go to this calculation, and we want the e-magnetic loss coupled with the thermal. So this is a electromagnetic thermal coupling simulation. You can see, yeah. So we need to solve the e-magnetic first. So okay, for this e-magnetic, I want the shaft speed to be 1000, and peak current we change to 344.5, and the piece is 41.03. And then what else we change? So we want to see the on-load torque, and we don't want to see this too, but yeah, we can take this. So first, we solve this magnetic model first, so that we can couple it to the thermal. And now we click on solve. It will take 5 seconds for this to simulate. Now you can see the thermal solved. Next, we go to the we go back to the thermal, and for the calculation, the input data, we go to the losses. So you can see these are the losses model from the electromagnetic coupling, electromagnetic analysis. So we unclick this speed dependent losses, and we want to see the copper loss vary with temperature, and we go to yeah, the temperature is 65. Yeah, this is correct. Now we go to for the thermal analysis, we go to calculation. You can see the shaft speed is the same from the electromagnetic simulation. For the first analysis, we want to see the steady state. So we click on this steady state. And for the model, we use full model, 3D model default here, and the steady state coupling we coupled with electromagnetic losses from the previous simulation. And now we can click on this soft thermal model. So now the simulation is very fast for this model. You can see it's already simulated. So this is the overview of the schematic of our model. You can see all the temperature here. And if you want to see for the radial view, you can see here. So these are all the temperature, the simulated temperature of the thermal losses here. Okay, and we can also see the axial view of the thermal losses. And this is for the what we call this is for the analytical result. You can also see the output data here, the losses. So this is the numerical result for the temperature here, the losses here. Well, so we can see the losses, temperature, the exit temperature, and the heat transfer coefficient, the thermal resistance here, thermal capacitance, the winding, the housing water jacket. So these are all the numerical result. Next, what we're going to do next is we see the simple transient simulation. So this is for the steady state. For doing for the transient simulation, we want to see this. We click on the calculation tab. We change it to transient. So everything else we put this is the same. So from we can see the transient tab here, and for this transient tab, we can change the. We'll be staying into a simple transient here. So we want the duration to be 7200 seconds. And number of points, we want 20 points here. So we see this user-defined loss. And for the initial transient temperature, we want the whole machine as specified temperature here. We change the machine temperature to 60 degrees Celsius. And then that's basically it. We just go to the calculation and we simply click on soft thermal here. You can see here the thermal tension calculation started. So these are the progress bar. So within seconds, you can already see the transient graph. So this is the graphical result for the transient graph. You can see all the temperature of the ambient housing, active housing, all this, and cap, the magnet, the rotor surface, the end piece, the rotate, the winding. So these are all the result you can get. And we also can see the power graph here for the transient graph. So for this transient analysis is the same as before. We can see the output data. You can see the losses, temperature, the heat coefficient, the thermal resistance, the winding, the housing water jacket, and we can also see the temperature. Yeah, we can also see uh, the temperature here, the losses here in schematic, radial, and axial view. Same as for the steady state analysis. So we can see this simulation is very simple and easy to use. It's good for rapid prototyping if you want to see, if you want to make a quick change in your design. If you just simply change a simple, you can just, it's a template based, right? So you just change the number here, and then you get a new and different model of the motor, and you can simply see the temperature as fast as it goes. And so that's pretty much it for the steady state and transient analysis for this BPM motor using Motor-CAD. And if you have any question, you can ask me now, or you can type in the chat box, and I'll give the screen to Zuleika for the of this webinar. So Zuleika, you may take the screen.
Mr. Farhan. Thank you very much, Mr. Farhan. Before we move to Q&A session, I already launched a poll. Please select the appropriate response and click submit. Now, it's time to address your question. Feel free to type your question in the chat features, which you will find at the right of your screen. We will do our best to answer as many questions as possible during this session. So, does anyone have question regarding this topic? While we are waiting for question to come in, I like to remind our participant that sometimes it takes a moment for a question to be formulated. Do not hesitate to ask about anything related to our discussion today. It seems that we might not have any question at this time, but that's perfectly all right. Sometimes topic can be quite comprehensive and may not lead to immediate queries. Rest assured, if you do have any question later, you can always reach out to us via email or our social media channel. So, Mr. Farah, is there anything else you wanted to cover?
So as we know, this is our second webinar for Motor-CAD. So if you got any of you guys want to see our the first webinar for the Motor-CAD, so you can reach to us or through our YouTube channel, and you can see our first series, which is the electromagnetic analysis for Motor-CAD. So I think that's it from me.
Great. Thank you, everyone. We appreciate you being here. And we also encourage you to connect with our social media to get the latest information. Thank you all for attending. We hope you have learned and enjoyed this presentation. Have a wonderful day. Thank you, everyone.
All right, thank you, everyone.